Hello, everyone. Last time we worked on our interpreter, and we wrote a simple interpreter for these if expressions. But now we're back to the parser, and we're extending the grammar that we're able to parse to include unary and binary operators. So this would be an expression that we can now parse. So note that, again, binary operator expressions always have to be parenthesized. So we don't yet have to deal with operator precedence. Operator precedence being that, for example, the multiplication is has to be parenthesized first. So for example, 1 plus 2 times 3 in most programming languages is interpreted as 1 plus and then 2 times 3. In our case, we will have that later, but not yet. At this point, this rule says that this always has to be parenthesized. So you can't even leave out the parentheses. So that makes the parsing very easy. And take a look back to our parser. We have this switch here where at the start of an expression, you read the first token and we decide on which of those rules apply. So we started out with the integer rule and with the if rule. So we were switching on token integer and token if. Now we have another rule that starts with a unary operator. So that's one of these. So I can just add this case here, case token not, I hope that's how I called it, and token negate. So this is this case. Should let me here. And then we have the binary operator case. In this case, we start with an open paren. Open paren. Let me check that was actually what the tokens were called. I think I have them here. Token negate, token not, and token open paren and close paren. Correct. Now all we have to do is do the recursive descent parsing again that we did last time. Let's look at the unary operators again. So we have already consumed the unary operator, and we are left with yet another expression. And we know how to parse an expression. We just call parse expr, right? So somewhere in here, we're going to call parse expr in context. But first, we're gonna allocate our syntax tree node. And if you recall the way I defined it, we now have a case for unary operators where we just put the token type in there for the operator. And for the binary operator, we have the same thing, except that we have a left and a right instead of just an operand. And also we have a token type. Let's go back and allocate the expression. It's an expr. Yes, it's an expr unary. And then I can just say unary dot operand equals that. And that's it. I'm done. That's a unary operator. And now for the binary one, well, no, I'm not done because I haven't put the token in. Binary, put it off. Yes, the operator is this token t.type. So here, we don't get any information out of the open paren. It's just there, just like the else or the end in case of an if. So we do, however, now have to parse one expression. Then we have to consume a binary operator, and then we parse another expression. And then we parse a close paren. So let's first allocate our parse tree node. This is a binary. And yes, so in this case, first we parse the left branch. And now we consume a binary operator, token t. So we definitely, I'm just going to put it into t. T equals scan context. And the thing here is now that I kind of want to make sure that it's a binary operator, but I think I have set up my, no, I have not. I haven't, I don't have defines for distinguishing binary operators. I only have first operator and first keyword and single letter operators, but I wonder. So let's take a look at it. So we have open paren, close paren. Then we have not, which is unary. Less is binary. And then negate is unary again. Sign and equals. Okay, so what if I move this around a little? Now the problem is, of course, that I should finally make a. So all I want to do is I want to have them in one chunk, so that I can do this same trick again, where I can say token first unary operator, token last, or binary operator. And the two that are not in line are, so it starts with less, right? Less is fine. Plus times the negate again is a binary one. And this is a unary one. And this is a binary and this is a binary, but a sign is also not even an operator. So basically I need to switch these two around, and then I need to move this one up here. But first, if you remember, I did this ugly thing where so one of the problems is that these are the single letter operators. Yeah, remember when I wrote the scanner, I did this because I was lazy, and of course now it's now I'm having trouble with it. So this needs to be the exact sequence as these are, right? So if I move the negate up here, not negate, and this needs to be after not. So that's good. But then I also have these operator names. So I have actually two places where I need to move things around. This is really not good, but I do a lot for laziness. And so now the only thing that's left is to move the assign out of the way, but I wonder. I think I can just move this one here. to do that, then I should actually have all the binary operators here in one piece, right? So they go from less, so we have less, plus, times, logical and, logical or, equals. Are those really all of them? Let's take a look at the assignment. Logical and, logical or, less, equals, plus, times, yes. So let's now do this first binary operator equals token less. Token last binary operator equals token equals. Now all I need to do is, here in the parser, I'm just going to assert that t.type. T.type. Actually, when I did these defines last, yeah, okay. Larger equal token first binary operator and t.type lesser equal token last binary operator. So now at least I catch the error. I don't handle it gracefully, but I'm sure that I'm not parsing anything that's not correct. So now I've consumed the binary operator. Next is the second expression, the right branch of the expression tree. And also what I can do is I can put the operator in equals t.type. And now I need to parse the close paren, which I can do with expect. I know what's coming. I know it's a close paren. And that should be it. Done. Now, of course, we did a few things here. Especially, I messed with the scanner, so I should rerun the scanner tests. So let's go to main. And remember, we had this scan main. So instead of doing the eval main, I'm going to do the scan main. Of course, I should write a command in parser to distinguish between them, but I can't be bothered right now. Use function. Okay. So now let's test this. So we have the scanner tests. I'm going to do Python test.py scanner with, of course, this simplang. Assertion failed. Function scan main. Line 24. Okay, that's interesting. Line 24. Really? Token type is operator. That's interesting. Okay, let's see what happens. On ident long. Really? Scanner ident long. So ident long is, as far as I know, just one long identifier. Let's see what's in this file. Okay. So it is actually a correct simplang program. Well, yes, it is a correct simplang program. So apparently we finished with the identifier works, but then we get this equals. So we did mess stuff up as expected. Oh, wait. There was this other thing, parser compiler.h. Is this still correct? Oh, no. Okay. Token first single letter operator. This is what we messed up. Also, we messed this up because the equals used to be The last operator is now a sign. And again, it's not really an operator, but we kind of treated it like an operator in the scanner. But this also we messed up. So open paren and negate are the single letter operators, but now it's times. Wow. So these are now the single letter operators. And because I moved the negate from down here up there, I had to update that. Okay. Let's try that again. Okay, that looks much better. Let's see, it runs. Okay, zero failures. So we're back to working. Now we can focus on the parser again. And actually let's call the parser here, parse main. And we have to update the print expression because we now have two more cases here. We have the unary and the binary. What am I doing? Binary. And the way we print them is very similar. If you look at the assignment, you just print the name of or the text of the operator basically, and then we indent the left and the right, or in this case the sole operand. So luckily, to get the name of the operator, we've already written a function for that, except that it was private. So it's called token type operator name. I'm going to make it public and put it in the header file. Token. Oh, it's already in the header file. That's weird. So this should not be. Why are these in the token type operator name? Wasn't that a static function? How does that even work? Oh, const. Ugh. My brain thought that was static. Never mind. It's all good. Yes, so we can already use that. We have the token type operator name. So all I need to do is printf, print the operator, token type operator name of expr v unary dot op, and then print the operand, unary operand with one more indentation level. And for the binary, almost the same thing. And then we have the binary left and binary dot right. And that's how we print the tree.
I think there's an F missing, right?
So let's try that out. So actually, one thing we can do is we can test this. No, that was not good. Implicit declaration of print, where they use print. I can use the test cases for the previous parser assignment. Those should still work. So I'm gonna run this on parser 1.4, 1.2, and they do work. Now let's try that. I was lazy and there's only one test case, but it's a complex one. Hooray, it works. So as you can see, if I test parser 1.4 x.sl, that's the one from the assignment. And if we run it, test parser 1.4 flex. So we get exactly that. And that's the parser. So then, next time, and note I said that I'm away for a week, so we have you have almost 2 weeks now to catch up. And the next call is, I think, in 13 days. So anyway, I should show you this in the proper. That was not what I wanted. And the proper markdown syntax, because it looks ugly here. So in assignment 1.5, we need to again go back to the interpreter, and we're going to interpret these expressions now. So what we need to know is, how do these operators work? And that's what this does, but I'm gonna explain it. So this is the logical not operator, meaning that it interprets X as a Boolean, so 0 meaning false and everything else meaning true, and it logically negates it. So if X is 0, meaning if X is false, then you get 1 as a result. And if X is not 0, meaning if X is true, you get 0 or false as a result. Minus is the arithmetic negation operator. So that just means that 3 becomes -3 and -5 becomes +5. And note, by the way, that all of these operators have to work on 64-bit signed integers using 2's complement arithmetic. If you're using Go or Java or many other programming languages, that's what already happens. If you're using Python, Python uses arbitrary precision arithmetic. So basically numbers can become as long as they need to be. You would either have to do your own 2's complement cutting off or something to make that work, or you can just use NumPy in 64. I'm using C, so I also get that for free. But it does mean that some things are weird. So if you're not familiar with 2's complement arithmetic, you maybe should look it up on Wikipedia, because that's how computers work internally, and that's good to know. But weird things happen where, like, if you add 1 to a really large number, suddenly it becomes a really small negative number, or like large in magnitude. And there is one number that is its own negation, which is also weird. I think that there's an example even, maybe. So here's an example of really large number plus 1. So this is actually 2 to the power of 63 minus 1. And then you add 1, which causes an overflow that is ignored, i.e. the top bit is cut off, and you get a negative number. This is a trick from C, where if you want to interpret an integer as a Boolean, but you want the Boolean to be either 0 or 1, then you can logically not it twice. That's the bang. So you get, first you move it from 1 to 3 to either 0 or 1, but it's logically negated, and then you negate it again, and you get the right answer. So back to our operators. So now these two logical ands and ors are a little bit special in that they use short circuit evaluation. You don't completely have to implement this. You don't have to implement it yet for these inputs to work, but you might as well because it's not really hard, and later on we'll need it. So this is logical AND, and it again interprets integers as booleans as usual. And that's 0 if one of the two is 0, right? So if either x is 0 or y is 0, or both of them, actually, then it's 0. Otherwise, it's 1, and the otherwise being both of them have to be not 0. And short circuit evaluation means that you evaluate the left operand first. And if by evaluating the left operand you already know the answer to the expression, then you don't even look at the right operator. So basically, if x is 0, we already know what the answer to x and y is. It's 0. So in that case, we do not evaluate y. We only evaluate y if x is not 0. And the same thing with the OR. If x is 1, we don't, or if x is not 0, we don't have to look at y to know that x or y will be 1, right? So don't evaluate y. And the reason why this is relevant later is that y might be an expression that depends on x being false in this case. Or in this case, y might be an expression that for it to work might depend on x being true. So if x is false, y, for example, might loop forever and the program will never finish. And your interpreter is incorrect because it shouldn't have evaluated y. In other programming languages, it might be a thing where, like, you might have, for example, in C, you might write an expression if P is not null and P dereference X is larger than 0. Right? If P is null, i.e. if this is false, then this must never be evaluated. Because if it is, the program will crash because you can't dereference a null pointer. So that's the reason for that. Less is pretty straightforward. It gives you 1 if x is less than 0, if x is less than y, otherwise 0. This gives you 1 if x and y are equal. This is the sum, again, with 2 64-bit signed integer, 2's complement arithmetic, although signed and unsigned is the same. And same thing here, this is the product. So here are a few test inputs and outputs. I think this is pretty straightforward. We don't have a binary minus operator, so to actually do minus, you have to write plus minus. So this is the unary plus, and then the binary plus, and then the unary minus. Note that we don't have to write parentheses around this, right? Because it's well, basically because the grammar doesn't say so, but there is no other way to interpret this expression. Inputs, yeah, this is overflow. This is multiplicative overflow. So basically this becomes the largest negative number, which means that only its very, very highest bit is set. And if you multiply that by 2, that means a left shift by 1, and that means you get 0 because no other bits are set. And yeah, and that's it. So you got almost 2 weeks. Have fun.